Welcome to this unit 7 and 8. We look at curves, parametrized curves, and arc length and curvature. Very exciting topic where really calculus comes in. We will use the fundamental theorem of calculus, the definitions of derivatives, and so it's a very exciting topic. So first of all, we have the parametrization of curves, either in the plane or in space. And we have already seen that in the context of lines, but we have much more possibilities to define curves. This is a very important example. The case of the circle given here is a spiral. So we look at lots of examples. Then a very important moment is when we start differentiation. So differentiation, you should be familiar what the derivative is of a function of one variable. So now we have vector valued functions, and we differentiate a vector valued function by just differentiating each part. So for example, if we have which gives us a circle, because cosine squared plus sine squared is equal to 1, then we have r prime t. This is minus sine t cosine t. And we can continue differentiation. That's what we call the acceleration. This velocity has an important property that it's tangent to the curve. And I'm going along this vector here, that's my velocity vector. And the paradox is due to Zeno. Let me just mention Zeno here. And Zeno was thinking like this. So what Zeno argued is, if you have an arrow moving, and at every moment of time the arrow is at a fixed position, how can it move? It was solved by calculus, so it's a limit. Same definition like we have seen for functions of one variable. Now we have just vectors. This is a vector. And then there is a reverse process, which we know the inverse operation of derivatives. Taking derivatives is taking integrals, and when we do that, for example, we have the velocity given and we want to integrate to get the position, we can do that. And it's just the same thing. Everything is exactly the same than in single variable, except that we do it in parallel with all the components at the same time. And you can do that also with two steps when you have the acceleration given. It's very important. Acceleration is often something you know, that's a force by Newton. And then when you have the acceleration given, you can get the position by just integrating twice. First integration gives you the velocity, second integration gives you then the position. So it's pretty cool. That's maybe best illustrated with a free fall problem when you have the acceleration vector is constant. Usually we take minus 10 because that's what you have on Earth, the acceleration on Earth. When you do that, you can integrate that up and you get a beautiful parabolic motion. So one of my favorite is this, you take a straw and then you take these little balls here and you can shoot. And the nice thing about this magnetic, not bad, better, absolutely cool. Perfect. So now I have a good shot. What actually happened is these pebbles, they were shooting out here, and they gave there was an initial velocity, and it was attracted to the Earth, falling along a parabola. I'm Swiss, and we have this famous story of Wilhelm Tell. Whether it's true, it doesn't matter, but it's around 1307 that Wilhelm Tell was not greeting the hat of Gessler. Gessler was just asking that everybody greets his hat, which was on the street, and so he did not do that. And so as a punishment, because he didn't greet the hat, he had to shoot an apple from his son, Walter. So let's just see whether I can actually shoot the apple. Usually the apple is, take a real apple on my head and then students can shoot me. So that's kind of more interesting. So now I have kind of here Walter. I hit it, but it was just it didn't stick. Now about arc length, this is one of my favorite lectures because calculus comes in here. What you have to do is you have to approximate the curve with a polygon. And what I wrote you down here is the length of that polygon. So it's a sum of all these lengths. So it's this length plus this length plus this length and so on. The length of a little piece is just velocity times time. Time is 1 over n. Speed is r prime. Speed is the scalar. I should have said that. That's the definition of Riemann sum. A Riemann sum converges to an integral. So what we are going to do in class, we are computing the arc length for various cases. A very important property of arc length is that it's independent of the parametrization. So if this is a curve, it's a closed curve, and it's a toroid curve, and if you compute the length of this curve, it doesn't matter how you parameterize the curve. So you can go fast or slow. Length of this link is well defined and independent on how fast you are going through. And then a very important and very exciting topic is the topic of curvature. Curvature tells you from a curve how curved it is. If I'm walking around, I have a velocity vector which just points in the direction of my nose where I go. So what I can do is I can take this velocity vector and I can scale it so that it has length 1. This is called t. That's the unit tangent vector. And then we look how this unit tangent vector changes. So if I'm moving around here, around this circle here, you see kind of the direction that the vector, this unit vector, really changes. If I'm going faster, of course it changes faster too, so we have to compensate this. And then we get something which is just depending only on the geometry. And that's what we call the curvature. So for a circle of radius r, that's kind of important. The circle radius r has curvature 1 over r. A line, for example, has 0 curvature. And there is a nice identity which we are going to prove in class, which relates us with something we have seen in the first week. It's the velocity vector cross the acceleration vector over the velocity vector cube. It's kind of a little miracle that this works. So if you, for example, if your acceleration vector is the same or parallel to your velocity vector, that this means you're accelerating the same direction than you are going. You don't change direction, so your curvature is equal to 0. I mean, one of the applications of curvature is caustics. Let me just illustrate this because that's something I cannot do also at home. Say, for example, you have a glass or this is a sphere here, and you shine light through it. Here we have kind of a diffuse light, but if I take my foam, these are called caustics. You see kind of curves which happen. These are places where light focuses. A beautiful, now maybe you can see it here. For example, you're doing in the homework, you're looking at the caustic, the coffee cup caustic. If you look in your coffee, you see this caustics on. And finally, we look at the T and B frame, which is a natural frame associated to a curve. It's best explained maybe with a moving object like this drone here. So what you have is the unit tangent vector. The direction of the normal vector is n. So this is just t prime because this goes over, if this moves over like that, this n and t are perpendicular. And finally the b vector, that's the b normal vector, is just the cross product of the t and the n. This drone here has a lot of mathematics is involved. So I think that's it for today.